this is a slide that we already saw at the end of the previous class. So what we will do right now is to just look at one aspect which I forgot to mention during the previous class, which is this thing that you see over here. Are you able to see what I'm able marking on the slide?
Yes.
Yes.
Okay, great. Okay, so that's the space-time warp, which Einstein brought about in his general theory of relativity, and that's something that was something that we know always. I remember in the first class itself, we mentioned that space and time, that is x1, x2, x3 from the space point of view, which 3D that we are looking at, and the time are all independent variables, the four independent variables, so they behave in a very similar manner. And once things start increasing in terms of speed, there could be a warping in the space-time field, which is what you see over here. Okay, so this is another proof of the fact that time and space behave very similar to each other, which I just forgot to mention last time. So that's why I just wanted to come up with this slide again. Okay. Now, we will start looking at very briefly the history of dynamics, typically as seen by the Westerners. And can you just mute all your microphones, and we could probably unmute whenever it's necessary. I think everybody's muted except Najapa. Yeah. Okay, great. So let's continue with this timeline. You see that what is marked over here is a scale on the top, which is going all the way from minus 1000, which refers to 1000 BCE, written in with a negative number, what used to be called as before Christ, but is now commonly called as before the Common Era. And what you see is essentially the current century or millennium that we are going through. And in this, you see that though in green you have the mention of quite a few people from the Renaissance period, and then going back to the Middle Ages and eventually Greece and Rome. Hardly anything is mentioned in terms of actual names for Egypt, Mesopotamia, and Asia, which was the most ancient civilizations of humanity. And that's where I like to spend a little bit of time in today's class. And for those of you who are interested outside this class, we could probably look at it in a little more detail. Okay. But what is actually essential from this particular course point of view, AE2220, is essentially this blue shaded portion that you see over here that I'm marking as AE2220. And you see that uh, uh, just note that I might not be looking at the time screen if you're raising a hand or something. So whenever you feel like asking a question or something, just unmute yourself and ask so that I can respond to you, okay? Because I'm just focusing on the slides right now. Okay, so AE2220 is essentially going to be focusing on just about 100 years, or at the most 300 plus years from the 17th century all the way up to the 20th century that you see, which is when Newton came up with his laws of motion, and also which was a part of the Principia in 1687. That's the basis for most of this particular course, though there were quite a few developments in the variational principles perspective, which were also included in the methodologies of the West, and which is also included as a small portion of your text, which we will see based on the availability of time towards the end. We will try to cover that as well. So it's not just mechanics which got into prominence during these 300 to 400 years, but also a lot of electromagnetics, which we also said includes light. Okay, though light was understood in a different way in optics in the form of photons or particles of light, more as the waves of light. It was essentially during the periods of Maxwell, etc., where the actual equations of electromagnetics was brought up, and light was seen as a small part of the entire electromagnetic spectrum. Okay, and of course there were quite a few other names in the field of electrical fields as well as the magnetic fields, which were are some names might be familiar to you because some of them are used as symbols of or units of different quantities that you see, even Faraday for that matter, ampere for current, Coulomb for charge, volts for the voltage, that is the potential, electric potential, and Faraday for the capacitance, etc. Right? Newton, of course, for force is the SI unit. Now, let's just broaden our horizon and perspective a little bit, because this is also something that the Westerners do talk about in their general theory of science, physics, and in particular mechanics. And we will go backwards to see what exactly happened. Unfortunately, many of these people were religiously persecuted because in the West, religion was seen as an anathema to science, and anything that the scientists came up with, which didn't agree with the dominant religious versions at that point in time. The scientists were either put to death or they were exterminated and sent to places where they were never heard of from then on, right? But nonetheless, a little bit of what they have done still remains with us, and a lot of that continues to be used. For example, you are very familiar with Copernicus's heliocentric theories, where he looked at the sun as the center of the solar system rather than the Earth as the center of the solar system. Very interestingly, this is a question of the observer and then again the frame of reference, because it's the frame of reference which kind of determines the what is actually the center, because when you're having a frame of reference, that doesn't move because that's the where the observer is, and the rest moves. So most of us scientists, at least at that point in time, were all on Earth, and therefore an Earth fixed frame of reference would look like everything else is revolving around you, and that's not wrong as long as you are very sure about or clear about mentioning the frame of reference, and all your derivations, etc., taking care of that fact that it's an Earth fixed frame of reference, as we do even today. But it's all a question of relative motion, and that's where the ideas of Copernicus were very, very critical in coming up with the what we call as the heliocentric, because helio essentially refers to the sun. Helios means the sun, and therefore helio is an adjective related to the sun. So it's sun-centric, right? And even a little after that, we had Galileo, of course, did a lot of observation on telescopes. So the importance of observation becomes very, very critical over there, using telescopes, of course. And he and many others led to Kepler coming up with the laws of planetary motion. So remember that all of this is prior to Newton and the Newton's laws. So this is something that was kind of a bedrock or a foundation for what Newton did later on. And you go a little earlier, there were a lot of mathematicians too who did a little bit of physics as well. Fibonacci, you're familiar with, some of you might be familiar with the Fibonacci sequence, etc. Not of too much of a consequence for what we are going to do in the course. There was a lot of work from the West Asian countries, especially the region of Iran, which was then known as Persia, and then, of course, many other Western European scientists. In particular, something that really stood the test of time for almost really more than a millennia is the ideas of Aristotle. I'm saying ideas because a lot of things that he did seemed like mumbo jumbo to the people who came in the 17th century, including Newton, and what they thought was they were kind of disproving what Aristotle had held. as true for more than 1,000 years. But later now, we tend to find out if we look at the kind of language which was used in those days by the ancients, there was a lot of symbolism in their language. Things were more figurative rather than very objective. And for which reason you would see that many things which Aristotle said are still valid, but just that it has to be interpreted in an appropriate way, keeping those times in mind. In fact, we continue to use even Euclidean geometry. As you know, that is the geometry which is the basis of a lot of the work that we do. In fact, we will come to other people like Rene Descartes, etc., in the next slide. And this is just to give you an overview of the a much larger period, because we're stretching all the way from about 1,000 years before the Common Era, all the way to 2000 span of about 3,000 years, in which we are zooming in on about 300 to 400 years. Again, there's a lot of work, and many of this was a combination of physics and philosophy, which is why even today, we continue to call the highest degree that we award, whether it's in the sciences or in the engineering, as the Doctor of Philosophy, which essentially means that you're able to understand and add value to whatever is the body of knowledge that is already existing. Okay, there are quite a few others also. I'm not going into the details of that. Uh, what is actually left out in this is, even though we, to some extent, give a lot of credit to Aristotle, and duly so, there's also a lot of mockery of what uh, he did. And are you guys able to hear me? Just thumbs up will do. Yeah, okay, great, thanks. So this is as far as this particular timeline is concerned. I'll just go through the same thing from different versions of how the different people in the West actually looked at it. So there will be a little bit of overlap. So I'll not take too much of time in the next few slides. Let's see what we have over here. Right. So here again, we are talking about just that zoomed in period, so that we can have a little more focus on the foundational aspects of what we are going to study in this particular course, because that's the period of Newton, though here it is marked as part of the color, and therefore the electromagnetic spectrum and the discoveries related to that. We know that he had a huge contribution along with Leibniz to calculus. So these two guys did a lot of calculus, apart from the mechanics that we know today, right? Mechanics more from the perspective of Newton rather than Leibniz, but there's also a lot of theory which is to the credit of Leibniz, because at that time there was something called the vis viva dispute, which in Latin essentially means something which is associated with life force. So that's what it literally means, by which actually we see now, based on the expressions that they got at that point in time, what they were talking about is either the momentum or the energy, in particular the kinetic energy, that they were interchangeably trying to use. And it's understandable, because one of them, the momentum, remember, if it's translational momentum, is having the units of mass times the velocity. So it's like an mv kind of a dimension that it has, where v, of course, has L by t. And on the other hand, the kinetic energy, as you know, the expression is half mv square. Okay. So the dispute was not about the half factor, but mv versus mv squared. So some people believe that mv is the governing aspect of everything, and mv squared is the governing aspect of everything, was the thing that the other group was believing and therefore propounding. Most of them did not have the proofs, the mathematical proofs, or the physics-based proofs, even based on observations. At that point in time, it was mostly conjectures that people were coming. And in this sense, Rene Descartes plays a very, very important role. And today, a lot of things that he did, people laugh at. But there are a few things that he did which we continue to use, which in particular is the Cartesian coordinate system, which is named after him. So where he was talking about textural triads. So that is, if you have x1, x2, and x3 along three mutually perpendicular axes, then you introduce unit vectors along each one of them. Let's call it B1, B2, and B3. Okay, so then the idea was that if you take B1, B2, and B3 perpendicular to each other, it's very clear that if you dot any two of them, which are not the same, then it is essentially zero. And if it is the same, it is one, which together we introduce a quantity called delta ij, which is called as the Kronecker delta. And this delta ij, as you might know from some other courses, is zero when I equal to j, and is equal to one when I is not equal to j. And of course, I and j, like all other Latin indices that we will use throughout this course, when we're talking of three-dimensional space, will take on the values between 1 and 3, right? So this is integer values between 1 and 3, inclusive. Then, so that's all that remains of René Descartes, because this vis viva dispute that came up showed that the conservation of momentum is valid only when the net force acting on the system, the net moment acting on the system, that is put together, called as the generalized forces. Only if the net generalized forces are zero, that is the resultant forces, resultant moments are both zero, then your momentum is conserved. In one case, translational momentum, that is if there are no forces, or the forces add up to zero, which is what you did in statics, or what we call as the conservation of angular momentum, which is what you would have studied as part of the moment equilibrium. Okay. Now, what happens when there is net resultant force is what motion takes place, or if motion is already taking place, it has the possibility of changing because of an acceleration or deceleration, either in a translational sense or in a rotational or angular sense. And therefore, the orientation can change, the positions can change in a faster way. So essentially, you're talking of angular accelerations and the translational accelerations, all of which we will look at in the form of variables and equations governing them, etc., through the course as we march forward. But just to introduce the concepts in the context of history that I'm talking to you about right now, without giving too much credence to the equations involved. And that's where Leibniz, oops, that's where Leibniz is important, because not only along with Newton, he brought up calculus, but he also was a major part of this vis viva dispute in the transition that took place from the law of conservation of momentum to the law of conservation of energy. Actually speaking, the rear view mirror is always a great advantage that we have. And we see that now both had their own places. It's not that one versus the other. It's a question of understanding the validity of each of them. Because the way they were portraying it, they were not calling it momentum or whatever it's called as the power of life or life force and things like that. A lot of things were seeming like mumbo jumbo, because things, as I said, were distinguished between how we experience life and how science was studied. Whereas in reality, they can have a lot of commonality, which is what the ancient people were able to see. And with our myopic vision, where we divide things into smaller portions, we are not able to have that holistic vision, and therefore we try to find fault with some of these ancient people like René Descartes or Huygens or even Galileo and Kepler, Copernicus, etc. But even pre-Copernicus in terms of the geocentric kind of a model, which is very much valid because that's what we in fact use today for a lot of the aircraft dynamics for aircraft which are flying in the Earth's atmosphere. And similarly, when we launch interplanetary missions and eventually planetary explorations, whether it's in the Martian atmosphere or the Venetian atmosphere, etc., we are still focused on centering around those planets because that's the gravity which kind of predominates over the sun's gravity for that particular vehicle, and therefore a lot of physics can be understood by looking at a Venetian centric or a Martian centric kind of a model as well. It's all a question of consistency and making sure that you know or aware of what assumptions you've made, and therefore you're not stretching your validity of the theories beyond those assumptions. That's what is much more critical. Okay, but it's interesting as a story. The history of science is a very interesting history. It probably makes for a far more interesting movie than many of the Hollywood or Bollywood movies today. Coming to where this vis viva dispute itself figures in, you see it's the division between, on the one hand, Galileo and Kepler, whose most of the work was based on observations. That is essentially experimental observations was the key for that. On the other hand, um, the vis viva dispute, once it happened, and then eventually Newton came in, it was mostly mathematics, and in particular calculus. And later on, when Euler and Lagrange, etc., came in, it became the calculus of variations that I briefly talked about in the previous class. Okay, so then there were many variational principles which came up, which is the stationary principles of the in terms of whatever is the governing functional, and therefore we had the so-called concepts of Lagrangian, named after Lagrange, and the Hamiltonian, which if time permits, we will go through in a little more detail towards the end of this particular course, which can be shown for most systems to be derived from the Newtonian mechanics, but it's much, much simpler to implement because we'll be dealing with scalar quantities instead of vectorial quantities for the same problems. For very simple problems, it might seem like a stretch to use these the energy principles or what are known as stationary principles. But if you look at in terms of more complex problems, which is what we solve in real life, especially we as aerospace engineers, especially like space dynamics kind of problems, where you're looking at the interaction between various satellites, the interaction between a launch vehicle and the satellite, which is kind of separating from it, or something which is docking back, and things like that. All these kinds of dynamics are fairly complex in the presence of multiple gravitational fields, etc. And when you're having such a situation like that, we typically tend to see that these stationary principles kind of methods, be it the Lagrangian, Hamiltonian, or many others that were there. I will talk about, in fact, one of the pioneers, which was even before Lagrange and Hamilton in the next slide, and some of the next slides when we go to there. So these tend to be much, much more efficient ways of approaching the problem. The chances of making errors are also very, very less when you use this kind of an approach. Now, yeah, of course, there are many others as well, Laplace, Gibbs, etc., whom you would have also studied. For example, Gibbs, the free energy that he talks about, which is another way of looking at the stationary principles in a much more broader perspective, because he had the advantage of Lagrange and Hamilton prior to him in a historical sense. Then, of course, our focus here is on the mechanics and therefore the dynamics. And most of it is based on what Leibniz actually came up with. And he was kind of in between Newton, Lagrange, and Hamilton. These four names will keep coming every now and then in our course, because they are the important contributors to what we study as engineering dynamics and engineering mechanics today. But physics, as you know, is a much broader subject, and there's a lot of other fields as well. For example, we talk about electricity here. There are quite a few people involved, like Galvani, after whom galvanic corrosion, etc., is named. Then Volta, Ohm, after whom the unit of resistance is named. Then you see Faraday, we already mentioned, Gauss, Staines, Siemens, and similarly, since the electromagnetic spectrum, part of it is the light, the visible light spectrum. Um, Quite a few people who worked on that are also of great significance. And Newton himself, who had his explorations in multiple fields, and which is very important. Today, we are in fact getting back to that region of looking at multiple things rather than deeply specializing in something. Till about a few decades ago, especially around the year 2000, we had always this debate about breadth versus depth. That is, in research, should we have a broad spectrum of research, or should we have a depth in a particular area and go deeper and deeper into it? But over time, a lot of fields that we need to understand have been dug so deeply that digging further only gives you a very incremental kind of an understanding. Of course, there are branches of physics that we talked about as the chasm of ignorance, and what is not at all understood in 95% of the universe. I'm not talking about that. Even the 5% that we understand, there, most fields have been dug so deeply that you still can get some information if you're really good at the field. But if you want to make a big impact, especially as engineers who are more applied scientists rather than fundamental scientists, then you need to have a broader perspective and try to understand the multiple systems. And aerospace engineering is a classical example of that, because it brings in various other aspects of engineering into it, which is why a lot of professors and even people working on research in the aerospace industry are people with a bachelor's degree in mechanical engineering or electrical engineering, or even civil engineering for that matter, and many others, chemical engineering, etc., for combustion, etc., which you would have explored in some of your lab visits also. Some of those professors there are from some of those backgrounds. So you see the broad spectrum that is involved. And also, when I was introducing to you our lab, I talked about the multifunctional materials, in particular multifunctional composites, and we saw how the various physics, including electrical energy, the strain energy, which is mechanical, and quite a few other things like electromagnetics, which is important for antenna and radars, etc. All of those are things that are very, very critical in what we do. And the interaction between them, uh, unfortunately, cannot be through a principle of superposition, because each of these behaviors is quite nonlinear. And when you have nonlinearities, even in one of them, then it becomes next to impossible to just study them individually and then think of putting them together at the end. You have to, from ground up, from the very basic fundamentals, you'll have to start looking at how these things are actually done, how they interact with each other in a nonlinear fashion, because that's not trivial. It's highly non-classical and non-trivial. and that's where some of these people I really am impressed by, even in those times, like Newton, were looking at so many different fields. Of course, there are few things we people criticize about each one of these individuals, but like all human beings working in various fields, every one of these guys also had their strengths and deficiencies. So, and we also have to take a look at what their body of work is from the times that they were living in, and also the kind of exposure they had to other civilizations. Today, the world is a single global village, and anything that happens, unless it is highly proprietary within a company, most of the academic things that goes on in universities, etc., any new discoveries, etc., come to the fore throughout the world, and with the appropriate references, we can work on going beyond that in terms of a value addition. And that's how science has developed much faster, and therefore led to engineering applications also, which were unimaginable even a few decades back. So that's something that we are proud of, and probably should continue to utilize to the extent that we can. So, of course, there are other things coming from the light spectrum. We already discussed Maxwell, but also in terms of the standards that are there, like, for example, in the US, you have the NTSC standard for the television, for example, whereas in India and many other countries like Japan, etc., we have the PAL system. So, the distinctions between these, how these are utilized. There's also a takeaway from even radio waves, where we looked at amplitude modulation, or AM waves, and FM radio, which is frequency modulation. So how you have a carrier signal, and over that carrier signal, you're essentially loading something which is uh, like the actual information that needs to be conveyed by the carrier from the transmitter all the way to the receiver. And it's those things which went on from the audio to the video as well. And once again, you see, as I was talking to you in the previous class, everything is actually coming from the human being, because we are able to hear, we are able to work on all of these various audio technologies, the science of hearing, and then the audio technologies which go beyond that. And similarly, the in terms of the science of vision, and the color and the electromagnetic spectrum, etc. So since we understand lighting, which is again a very critical part of extending our work hours as well. Otherwise, people could work mostly during the sunlight period, which is the sunrise to the sunset. But the fact that we have artificial lighting for a long period of time now, and the various innovations there, all the way going to LEDs, etc. Have been in terms of energy efficiency and things like that, the ability to replicate color more realistically, and therefore the transmission or broadcasts which have been much more realistic than before. So let me, I'm actually skipping a lot of people, but they all have made immense contribution, just like Gibbs free energy there. There's also something called the Helmholtz free energy, even though Helmholtz is mentioned here as part of the electromagnetic spectrum. We use this also sometimes as part of a lot of our dynamics, in particular thermodynamics. Okay, now looking at it from a little more broader perspective, in terms of more important people who are usually ignored. And amongst these, we already looked at D. Lambert in our class in the on Monday, and one person who you will find pretty much in every literature of physics, in particular mechanics, and also a lot of mathematics as well, is Euler, one of the heroes of my advisor, and somebody whom he used to adore, and for the right reasons, because the broad spectrum of contributions he has made. Of course, Professor D.V. Hodges was a very staunch Christian, and he used to conduct regular Bible classes on campus, and he also liked the fact that Euler's was one of the few scientists of those times who was wearing his religion on his sleeves, and saw no contradiction between being religious or spiritual, more particularly, than and also being a scientist. And this is something which was there in the ancient past, even in the West. If you look at Aristotle, etc., even Socrates, more of a philosopher than a scientist. But you see, there was always an overlap between this, and there was no complete bifurcation between this, which happened in between. And again, people like Euler and even Einstein, for that matter, were people who really brought this back in a big way. But that's besides the point. What is very important from our course point of view is this guy, Maupertuis, who is hardly heard about today, unfortunately. I'll talk about him in a slide later in a little more detail. But he was the first one to apply the so-called stationary principles, including what was eventually the Hamiltonian, Lagrangian, etc., to problems in mechanics. I already discussed to you in a very, very simplistic way what was done in optics in terms of reflection and refraction. I told you that the either the distance or the time duration traveling for light to travel from point A to point B, either in the same medium after hitting another medium, or passing through the second medium. The kind of principle involved is the same stationary principle. In particular, there we were looking at a principle of minima, but even some principles are, especially depending on the way they are posed, could be principles of maxima also. If you're looking at the reciprocal of the functional involved, then obviously it becomes the maxima. And we know that the calculus that Newton and Leibniz in particular came up with helped us to take the first derivative and set it to zero in a calculus problem in order to look at a stationary quantity of a function. And we then looked at the second derivative and saw whether it is positive or negative, and depending on that, you had the maximum or the minimum, right? Uh, in calculus of variations, it's a little more involved. It's beyond the scope of your class, but that is what became the bedrock of the Lagrangian, Hamiltonian methods, etc., which we will see without going into the depth of calculus of variations, just from a point of view of the alternatives to Newtonian mechanics. So once again, you see, in terms of the major works or contributions that were there, I've been talking to you quite frequently about the Principia of 1687, which Newton wrote. But there were some interesting works, and many of these have English translations. So those of you who are interested in the history of science can look at this, because it's beyond the scope of this course to discuss some of these things. But many of these things were similarly some fundamental papers on mechanics by Euler, then the analytical mechanics that was done by Lagrange, the general methods in dynamics by Hamilton, and then you have this is a German word for essentially looking at the various aspects of dynamics by Jacobi, again a very important contributor to the stationary principles, which is the scalar equivalent of Newtonian mechanics. And similarly, again, extrapolation from solid mechanics to fluid mechanics, in particular gas dynamics, etc. And then, of course, Einstein came in and completely changed our perspective on a lot of things. But still, the validity of the prior work only shrunk it. It was not completely dismantled, so to speak. It's just that we have to be aware that whatever theories were prior to Einstein are essentially applicable for the lower speeds as we start approaching the speeds of light, which we haven't in aerospace engineering, at least as of now, though we have hypersonic vehicles much faster than the speed of sound. It's not anywhere close to the speed of light, which is a much larger quantity. So this is as far as, and of course, some very recent people like Feynman and his series of lectures on physics are extremely popular amongst the young crowd for the right reasons, because he puts it in a very, very interesting perspective in his lectures, and which are accessible not only for students of science and engineering like us, but even to a lot of laymen who are more interested in it from without the equations. In this context, I think some of you might be aware of a book by Kermode, which is Flight Without Equations. This is a very interesting book, especially if you are trying to explain what you understand of flight and aerospace engineering to people who are not with a very rigorous scientific or mathematical background in particular. Then the way Kermode describes it is very, very interesting. In fact, there is a quote which is attributed to Einstein, that I am not sure whether he actually said it or not, but there is some controversy on that. But the principle behind it is very, very interesting. If you what that quote goes on to say is that if you cannot explain what you're doing as part of your research to your grandmother, then there's no use of whatever you're doing, because it's something that has to be having relevance to the layman eventually, in terms of how it is applicable. And it's very important for us to not just brag about what we are doing by just introducing a lot of terminology, because many cases it's the terminology which becomes a barrier for newcomers and laymen to get into any field. Because if you break down that terminology and actually use more simpler terminology, then you will see that essentially we're all pretty much talking about the same concepts in high school physics, high school math. We're just broadening the horizon, having applications in very specific fields. When we are trying to narrow down those applications, then we start talking the jargon or lingo of that particular community, of a specific community. And for example, the aerospace community, or even within the aerospace community, a lot of what we helicopter engineers speak about mm, uh, may not be understood by the fixed wing people. For example, the swash plate, or the let's say the lag kind of a coupling, pitch coupling, etc. So some of these things are peculiar to some specialist fields. And once we understand or break down this terminology into what it really means in day-to-day language, or at the most high school physics and high school math, then most things are quite accessible. Uh, I'm stressing on this in particular because I think Tilak mentioned that dynamics is one of the most difficult courses. Yes, because that's the way it's unfortunately being taught or written in books. But if you actually look at it from a more fundamental point of view, it's not way too much more difficult than what you see in high school physics books. And this I'm not saying because I've done research or have guided a lot of research students in this particular field, but more when I teach newcomers and how quickly they tend to grasp some of these aspects. I can see that the main barrier is the terminology or jargon or lingo, more rather than the actual physics or math that is involved. So just try to break it up and try to see the parallels from what you know to what you don't know. So it's that journey that is learning, which is very, very important. Yeah, even if you are attending a viva or an oral exam, or defending your thesis, etc. The people who come and ask you questions, whether it's in the committee, from the committee, or from the general audience, they're all coming from their own backgrounds. What have they worked on previously? What are the terminology that they are used to? And then they're trying to relate that to what you present, and therefore ask you questions in the overlapping region between them. So if you understand from the audience perspective, or the specific questioner's perspective, where he or she is coming from, then more often than not, you will have a much more convincing answer for them, which is what is a huge And again, this is not just the oral communication, but even written communication. When you eventually write papers, etc., uh, manuscripts for the journals, which eventually become, if accepted, articles in those journals. Again, it's a question of keeping in mind who the target audience is, what they understand, what kind of terminology they use, and therefore express what you have found or what you have discovered in that particular manner, right? Uh, can you just show me if you're not hearing any echo? Just show me a thumbs up so that I understand everything is fine. Okay, good. Thank you. Now coming back to yeah, maybe I'll just skip this slide because it's essentially saying the same things, but with a little more personal implication there and the specific topics. For example, in thermodynamics, we'll be aware of the role that entropy plays, etc., which we did not cover in the previous slide. It's part of thermodynamics, which is also kind of dynamics involving heat flow and heat transfer as well. And so there's nothing like too complicated about that unless the person writing the book or speaking about it tries to make it complicated, right? So, and similarly, there are applications to biology. So, a lot of things that we physicists or even mathematicians do, there's a lot of things that go on to understanding life as in its very first principles, starting from the DNA below. In fact, I had a research student who graduated a couple of years back who primarily worked on modeling the DNA. And even though I, as an advisor, didn't have a biological background, not having studied it beyond the grade 10. I could still correlate to once I went across the terminology barrier, I was able to look at it from a very different perspective. And that's what leads to value addition to the knowledge, small or big. So I'll just skip through these slides. And this is where I really would like to focus, kind of summarizing everything that we have looked at in the last 3 or 4 slides, but also bringing in something which, at least as of today, we know as the most ancient contribution to mechanics, which is going beyond the West. Because when I say in the West over here, I am talking about primarily, except for the first item over here. This is an exception, which is from the East, and in particular from the country that you're currently doing your study abroad program in, that is Bharat or India. Here, even 200 years before Aristotle, uh, there was text which I already showed a translation of earlier by Maharishi Kanad. It's called the Vaisheshika Sutra. So the Vaisheshika Sutra is essentially, Vaisheshika means something which is subjective, and Sutra is like a formula. So this is like a subjective formula, or since there are many of them, some formulae, right? So now the way these are done is extremely crisp, and there's a lot of interpretation for ambiguity, uh, and rightly so, because of the wide range of applicability of some of these topics. Like the right at the beginning of this course, I asked you all what you understand by dynamics, or what just hearing the word dynamics makes you think of. So when you were saying that, one of you even mentioned social dynamics, and very, very rightly so. And I said it then, and I repeat now, that a lot of things that we study as part of dynamics of so-called inanimate or insentient beings or bodies or even particles are actually uh, have a carryover to life itself, in terms of life dynamics of an individual and of the society and of the globe and the universe as well. And therefore, you will see that the subjectivity that is essentially involved, in other words, the observer. And most people think that observer just means the frame of reference, FOR, which of course is an important aspect of it. But the frame of reference, or FOR, is just the physical aspect of the observer. at the most you look at the intellectual or emotional aspects, but there's something beyond that, um, which is the metaphysical or the beyond physical aspects, which are also very, very critical. And many of these things, statements there are directly applicable there. I'm thinking of making a separate, shorter video on the original, because the Vaisheshika Sutras are almost like hundreds of stanzas. So there's no point in going through all of them, but just a very few that talk about these three laws, which are almost identical to the laws of Newton. And Newton, even in his Principia, and even as of date, nobody has gone into what was the proposition behind those laws. If the laws are just stated as they are without going into the proposition on whose basis these laws were come up with. Whereas Maharishi Kanada actually talks about those propositions first and then comes up with the laws. So there is a logic or a rationality behind how it is developed, and that's probably where physics and science are headed in the future. So those of you who are thinking of more fundamental research in physics or mechanics or dynamics would greatly benefit by looking at this, because this is not just history or ancient, but this is the future and the way science is progressing. Because, as I said, in the metaphysical aspect, the conscience uh, or consciousness is coming into picture, and a lot of debate about what is consciousness. A lot of people think about it as brain generated, but brain is also still a physical entity. At the most, it can be treated as an intellectual dimension, but consciousness is something beyond the intellectual dimension as well, which is where a lot of the future physics will be. The future, not in the far future, but even in the very near future, where the leading physicists are looking at the cutting edge of dark energy, dark matter, etc., to understand and close in on that gap of what we call as the chasm of ignorance. That I think is going to be closed in the near future, probably in your lifetimes, if not mine. So it's very, very essential for those of us who are at least at having that capability, because you're from one of the best schools in the world, and there is a possibility, depending upon what you eventually go for as a career. Uh, if you do industrial kind of jobs, or where you may not have too much of a say in terms of what you do, unless it is some of the top companies which have a lot of interest in the future, and therefore a vision for the long-term future, and therefore expend a lot more on research and development. More of the research, even if it's taking a lot of risk. So, but if you're especially going into the academia, then this is something that you cannot completely ignore, because most of the new developments in physics are going to be in that area. And of course, that is from the future point of view, but from the historical point of view, as I said, even 200 years before Aristotle, these were the, at least as of now, we know the original laws of motion. It's not saying that he was the originator of that. There might have been people even before him, that at least from historical records with appropriate proofs of the existence of this. This is as far back as we can go as of today. But there could be discoveries which take us even further back, and that Maharishi Kanada was probably just stating what was already known by people before him. Because Aristotle himself, in his work, the pioneer from a Western point of view, he says that whatever he writes is based on predecessors. Of course, he doesn't talk about the nationality of the predecessors, etc. But even if they were Greek predecessors, it shows that these were the bodies of knowledge which existed even more than 2.5 millennia ago. And we should not belittle these original contributions, but have to look at it from a different lens, the way we perceive it. If we are too soiled by our current understanding of science and then look at it, then many of these are ridiculed, which is what a lot of, unfortunately, Western scientists do. But there is a lot of takeaway from that, because even the energy methods that we're going to study, like Lagrangian and Hamiltonian, are actually coming from Aristotle, because one of the important things that he said, let me just clear some of these things. Yeah, one of the important things that he mentioned that you see here is all manifestations of nature follow the easiest path that requires least effort. This is a very, very important statement. And many people don't understand the implications of that, both from a scientist's point of view and from life's point of view. Because if you look at anything that happens in nature, all the way from how plants or trees grow and how they spread to other regions and how animals survive and how they've evolved from one kind of species to another, they're all essentially following the so-called easiest path that requires least effort. Uh, Whereas, unfortunately, in the recent past, over a century or so, there has been this current theory that there isn't a substitute for hard work. People always claim great pride in saying that uh, I work hard. Uh, he's a very hard worker means it sounds like a compliment for most of us. But this is essentially because these kinds of people don't love their work. Once you start loving their work, to put it in Steve Jobs' terminology as well, you never really need to work hard. The hard work is required only when the work that you are doing is something that you're not really interested in. So that's essentially important thing that I would like to convey. To put it in very strong words, I often tell my students this fact that people talk about there's no substitute to hard work is true only for stupid donkeys. Because donkeys, don't like their work and therefore do what is called as hard work. Because if you love your work, you become so efficient at your work because you build your capabilities towards doing that work. And once you have the right tools to do your work, then obviously you're just going to ace that. Okay. Uh, just that people think that putting in long hours working on something for 10 hours instead of 7 or 8 means that they've done a great job. No, not necessarily. Somebody within a jiffy might be able to solve something just because of the way they have a clarity of perception. And that clarity of perception is not gained overnight. You keep observing, 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 like what Galileo did or what Kepler did, etc., and what great Maharishis in India like Kanad did. They were looking at things from a much, much more fundamental perspective because they were able to spend hours together or days together observing something which seemed of no significance to somebody else or most people for that matter. That fact is what makes you start falling in love with what you work, and therefore you start taking the path of least effort, and that is the easiest path. And that's what one of, if at all we have to learn one lesson from Mother Nature, then that's to follow the easiest path, which requires the least effort. And that's a joy to work. Then you don't have this distinction between a working week and a free weekend when you're going to enjoy. Even your week when you're working is or studying is going to be as joyful or as enjoyable as what you're going to do in the weekend. Okay, so that's an important thing from a not only a philosophical point of view, but even science, the way we do it. And this is something that I inherited from Georgia Tech, from Professor Hodges, who was so always joyful in his work, and they used to get so carried away by whatever he was doing because of the total involvement. See, there's one thing about entanglement. You do not want to get entangled in something when you get into an attachment, and once again, it leads to hard work. But you're totally involved in it. And that involvement without getting entangled is what leads to falling in love with whatever you do, or what is called as devotion, because most people think of devotion as a religious terminology, but unless and until you're devoted to whatever you work on, whatever you do, nothing great can be achieved. All those great gentlemen whose names I mentioned in the previous slides, They were all devoted to their work, and which is why they came up with something that was so phenomenal, and we could still talk about that today, is primarily because of how much of work that went into whatever they were doing there. Okay. And 2,300 years ago, that's just about 100 years after Aristotle came up the subject that you already have studied as part of your first course in the series of mechanics, which is statics, right? So, and Archimedes knew the laws of statics, and um, this is 2,300 years ago. So, and nothing much has changed. Pretty much everything that you studied, irrespective of which textbook you studied from and who was the instructor for your statics course, uh, you will see that all of that was something which came from Archimedes, and hardly any change in the substance or the core of what he said um, has changed. But as far as dynamics is concerned, because people were not aware of Maharishi Kanad, therefore there was a long gap of about 19 centuries that you see over here between Archimedes and what we call as the golden period of mechanics today. All those guys that I talked about in 3 or 4 centuries, namely Galileo, Descartes, Rene Descartes, that is Fermat, Newton, Leibniz, Bernoulli. Again, Bernoulli, we have to be careful in how we qualify because it's a great family of scientists, and there are many Bernoullis. And then all of their last names are Bernoulli, and we think the same person contributed to it all. No, there are many, many different uncles and nephews and sons who all contributed towards that. Okay, so and another thing that you will be looking at is Hooke's law, because the Hooke's law is Hooke's law is something that you would study deformable bodies and also structural analysis, and that is also something very, very critical, which is having the flavor of mechanics built in, but in a taking it to a different directions in terms of the overall material behavior. In terms of the stresses and strains that develop and the correlation between them, at least for small strains, in terms of linearity in their dependence on each other. Now, coming to the Galileo principles, there are two in number, and which is what was the basis for Newton, whatever he did in the Principia. And again, it's also in the spirit of Euclidean geometry. And one of my professors, uh, actually collaborator, but a little senior and somebody who came from Russia and settled in the US, who was a professor at Georgia Tech for a short while before he moved out to a different university. Victor Berdichevsky, used to say that whenever we quote somebody, we have to give credence to the most original contributor in that field. There have been, of course, very important value additions, but most of these have been incremental in nature. The original is what is of greatest significance, and that has to always be acknowledged. So even though we keep talking about Newtonian mechanics, we should not forget that the source for Newton were Galileo's two principles, and also the framework, or the mathematical framework in which he put, which belongs to Euclid. So Euclid's Euclidean geometry is what is the spirit in which Newtonian mechanics work. So Galileo's two principles are not only the basis for Newtonian mechanics, but they are in the spirit of Euclidean geometry. Thus, Galileo and Euclid are very, very intricately correlated in terms of how they came up with their methodologies, though they were separated in time. And as of today, the way we look at Galileo, if you look at it, yeah, Najama, you had a question, you raised your hand.
So there is a bit of echo coming up.
Oh, I see. Okay, thanks for mentioning that. How about now?
It's still there a little bit.
Okay, let me try. Is it better now? Yeah?
Yes.
Okay. Okay,
Yes.
great. Thanks. Okay. So now let's look at Galileo's two principles. These is the basis for Newtonian mechanics and in the spirit of Euclidean geometry, as I said. But very interestingly, the way most scientists look at it today is that these are just mind games. As of today, the way we understand mechanics from that point of view, if you look at Galileo's two principles without actually going into his shoes or his glasses, so to speak, to understand what he was talking about, then these are just mind games because neither of these two principles can be validated. Remember, we were talking about verification and validation in the previous class. We said verification is with another theory or a computational method, whereas validation is with what we observe in experiments, either in reality or in a lab where you have controlled parameters. Even with controlled parameters in a lab, a validation of Galileo's principles has still not been possible. So it is that in that sense that we call these as just mind games. Okay, not just we, but the Western scientists in general treat Galileo's two principles as just mind games. Why? Let's look at it. The two important reasons for that. The first one is that the mechanics laws invariance with respect to the initial frame of reference. So this I here stands for inertial frame of reference, okay, IFOR. And we, in fact, in the previous class also discussed that there is no such thing as in reality an inertial frame of reference because inertial frame of reference is defined as one that is not accelerating. And if something is not accelerating, means its speed should not change, and neither should its direction change, because that is change in orientation or rotation that is completely left out, which essentially means a rectilinear motion, just like an aircraft which is cruising at a particular altitude. But even that, we know that because over a period of time, it's actually taking not a straight line path, but a curved path because the surface of the earth itself is having a certain curvature to it, and therefore it's going over that. Now, coming to the mechanics laws invariance, which is what Galileo built almost all of his theories on, that is valid only when you are referring to a frame of reference which is not accelerating or which is inertial, as we call it, which is a fallacy. Why? Because, as we already stated, such an a frame of reference which is inertial or non-accelerating, both in terms of the speeds and the which is the magnitude and the directions, is not possible. But I also mentioned that there are exceptions because of the fact that we as engineers are not looking at exact solutions. We are essentially focusing on what we are talking about within an acceptable level of numerical errors. And therefore, because the relative speeds or relative angular speeds of some of these entities that we are involved with are so different from each other that sometimes we can use, for example, even the Earth as a frame of reference and call it an inertial frame of reference. If you want to be a little more accurate, you have to use the sun as a frame of reference, which is a better inertial frame of reference, or closer to an inertial frame of reference than the Earth, because it's not rotating and revolving like the Earth does, revolving around the sun. But you know that the solar system itself is drifting across uh, in the Milky Way galaxy, and the galaxy itself is drifting, and the universe is growing almost indefinitely, which is something, again, a lot of the ancient Indian scientists already knew and have very clearly stated in many of their works, but now we are coming back to some of their findings. Now, the second principle of Galileo, which is also something that is uh, again a mind game, something which is dicey with today's scientists, because we still have not been able to verify that as well. And that's essentially what we call as the inertia principle. So what Galileo stated is that the non-interacting body's motion remains uniform indefinitely in unbounded space. This is where Newton got his idea, of course, for his first law. The first law of Newton is actually stating the same thing which Galileo did many years before him, but in different words. Okay, paraphrasing it, so to speak. And he had access to Galileo, unlike, of course, he might not have had access to Maharishi Kanad, etc., but he did have access to Galileo, and which is why whenever we write papers or we write books, we give a lot of bibliography, the citations or references from which we take knowledge. People think that one of the major differences between a religious way and a scientific way is that religion is made out of belief. In fact, many people call religion itself as faith, as these two words are interchangeable. But if you look at science also, the way we write our papers, way we write our books, we list a lot of references. And of course, we might criticize a few of them, but most of them we take as the foundation or starting point for what we are working on and what we are writing about. So in other words, there is this level of trust or faith or belief that is involved even in scientific work, because you take it for granted that whatever somebody has worked on before you is valid, and therefore I'm adding value to that or improving that or whatever. But there is some starting point. None of us go to the so-called fundamental or the start from scratch, because there's nothing like that, because everything that you start from has a background to it. So how far back would you want to go? If you go far enough, you are a scientist. If you don't go that far enough, you are an engineer. Or you don't go even that far, you are a coder, software engineer, so to speak. So this is something that you have to understand, that instead of criticizing people from other fields or other domains of work, you have to see where they are coming from. And essentially, we are also probably doing the same thing, but in a clothed or cloaked in a very different manner. So the inertia principle, which Galileo stated, is that if there are two bodies and they're not interacting with each other, then the one of those bodies' motion will remain uniform, because whatever speed with which it was going, including zero, of course, if it was static. So that's a special case. But if it's going at a constant speed and it's a rectilinear motion, that is, it's along a straight line, then you see that that will continue to be along the same straight line, and it will continue to be at the same speed forever and ever, which is what we call as indefinitely from a time perspective. And we are talking about because it has to keep on going. It has to be in an unbounded space as well. The space should not end, right? The way people used to understand universe till very, very recently, just a few years back, was that the universe has edges, boundaries. And of course, they knew it is growing, but they thought that it is ending somewhere. These funny things that even as late as the 21st century, the third millennium that we are in the common era, there is a lot of such faith or belief or trust amongst the scientific and engineering people. And all of these are fallacies, my dear friends, because that's something which cannot be proved either in reality or at the lab scale. Because why? Because isolated body is impossible. You can never isolate a body from something else. It's a question of level to which you isolate it. Maybe you can put it in a vacuum, have a free kind of a condition, but it's still in a particular field. So if it's in the gravitational field, then you probably conduct this experiment in space. A lot of work in space science or space engineering is not just about the launch vehicle and the satellite, but also the experiments that are conducted in the satellites which are in orbits. And some of these might take advantage of near zero gravity kind of situation and do some of these experiments. But even there, nothing is actually completely isolated. So it's a dream, it's an imagination, it is just a fantasy of scientists to think that something can be done in an isolated manner. Once again, of course, what comes to rescue, at least for engineers rather than scientists, is the fact that we are looking at now uh, relative things, relative orders of magnitude, and therefore say it's reasonably isolated. What that reasonably means, for some person, it might be acceptable. For some other person, it might not be acceptable, depending on what exactly they are working on and what they're trying to find out or prove. So isolated body is impossible. So leave alone, of course, unbounded space, which also we know today very well that it's just not possible. So since the very basic propositions or conditions on which these two principles of Galileo, namely the mechanics law invariance and the inertia principle, are based, and which in turn gave rise to Newton's laws of motion. Therefore, all of these are to be taken with a pinch of salt. It's okay for us as engineers, but if you're a scientist or a physicist working on dynamics, or in particular dynamicist, then you have to be very, very careful, depending upon the speeds that you're working with, depending on the sizes of the particles that are involved with. So there, of course, at least you have a way out in terms of the relativistic physics or the quantum physics. But even in the realm of fairly large objects, and also they're traveling at speeds much lower than the speed of light, there are huge errors which are possible, especially when you're looking at, as space scientists, aerospace engineers, you're looking at interplanetary missions or even intergalactic missions going beyond the Milky Way. Then many of these aspects become very, very critical. The errors involved in Galileo's principles, Newtonian mechanics, and even the many of the stationary principles which came out of it later on. Okay, now this was a huge gap, the 19th centuries, but led to a lot of engineering as we know today, because now science could be applied and applied to kind of problems and kind of technologies that we use almost on a day-to-day basis today, including the way we are communicating with each other right now. So we have to, of course, be grateful to all of that. Then 100 years later, that is about 300 years ago, is when, as I just mentioned in a previous slide, the very first guy to talk about variational principles as applied to mechanics. So people had applied to optics, for example, and a few other fields maybe, but Maupertuis was the one who brought it in for mechanics, especially to understand problems in dynamics. And that quantity that he tried to maximize or minimize is called as action. In his case, he was trying to minimize that. But in either case, what is usually typically looked at is the uh, first derivative, or the first variation, as we call it in the calculus of variations, which is the equivalent of derivative in the regular calculus that you are aware of. So that minimum action, if we want to minimize action, then we should know what is action. So action is given the symbol I over here, and you see that that I is given by I is equal to mass into velocity into distance, which might look like a very, very crude, meaningless kind of an entity. We understand mass into velocity, for example, is the momentum. That is fine. But what is momentum into distance? distance traversed, that is S. So it doesn't seem to have any meaningful thing, but that's how Maupertuis defined it. But later on, it was shown that these are things which led to the so-called Lagrangian and Hamiltonian, and therefore, indeed, it has some important physical meaning. We will not go back into history that much to understand this, but just that you have to go back to the definition of velocity as ds by dt, and then the overall um, action functional, which is the integral of this over a period of time. And then you see a little bit of algebraic manipulation, like some of the things that I showed on the whiteboard in the previous class. You will see that it comes to fairly familiar quantities. Or even if you check out the units for this, you will see what it might be tending to. But at least we got away from the vis viva dispute, where people were talking about life and positive life, etc., which is understandable, because when they're talking about kinetic energy, it is called as life energy, because whenever there is life, you think of some kind of a motion or movement. Of course, it's very evident in human beings. If they're not dead, we can move around. But even in animals. But some people might question, what about trees and plants? But even they might look like they're stationary, but remember that they're growing both above the Earth's surface and below in terms of the roots. So there is some kind of a motion involved. It might relatively be smaller and taking place over a longer period of time. The speeds might be smaller compared to the speeds of animals, etc. But there is essentially a motion which is taking place, a part of which is internal motion, like the blood flow within us, the flow of the sap, etc., inside the tree through the stems, and of course, all the way from the root to the leaves, and eventually contributing towards the generation of fruits, etc. Right? All of that, there is some kind of a motion, and that's what kinetic energy is all about. And kinetic energy taken at a much more micro scale is what temperature is all about, and therefore has a correlation with heat and thermodynamics as well. So that is all that life is essentially talking about, and which is why people use those kinds of terminology. So we have to be kind to those people to understand that from their perspective, or maybe we should be humble enough, because they saw something in a much more broader perspective than we are doing today with our kind of myopic vision that we have. Now, coming to this Lagrange and Hamilton, of course, we will come to it briefly towards the end of this course. But all of that, whether it is the very first one, Maupertuis, or Lagrange Hamilton, or hundreds of others which are there in the literature, they are all essentially stationary principles, which in general we call as the variational principle, because it's part of calculus of variations, where we take the variation instead of the first derivative, we take the first variation and set it to zero, and that's how we get this so-called governing differential equations, and either a boundary value problem or an initial value problem, or both. So that's something which has a history of just about 3 centuries. And the variational principle, there is an assertion that some quantity is defined for all feasible or admissible processes. And remember that in my interpretation of the story, the Aesop's fable, Hare and the Tortoise, also, I mentioned this feasible region in which you have to look for solutions rather than in the entire infinite space. And this is something that came up, especially when the variational principles came up, because you wanted to search for solutions within a particular range, and that's something that we use for various other branches of physics as well, which do not even use variational principles today, and it's also a very important part of mathematics in general. Now, what is that assertion? It's saying that amongst all those processes which are feasible or admissible, in other words, they satisfy the boundary conditions that are involved. They might be satisfying the initial conditions that are involved. There might be many such which are satisfying the conditions, but which of them actually is the correct one? If you are doing Newtonian mechanics, we know that we can actually have the solution of the governing differential equation go to the particular solutions by introducing the uh, boundary conditions or initial conditions. We can solve for the undetermined constants, etc. And then you have the final solution. But here, the way it is approached is that when you are minimizing this functional, let's say the action functional in the case of Maupertuis, or the Lagrangian in the case of Lagrange, or the Hamiltonian in the case of Hamilton, then you are searching from a large set of solutions, all of which are satisfying those boundary conditions or initial conditions, but only that one which will reach a stationary value for the real process yields the appropriate governing equations and therefore the boundary value problem as well, which is for the real process. There's one and one unique solution, which is the real process, and that you get to from the already from the infinite set. You have come down because of the boundary conditions and the initial conditions to a feasible or admissible set of solutions, and within that you then come to the real one, which is unique because it possesses a certain spatial structure. And here I come to one of my the greatest influencers of the way I think, as well as the way my advisor used to think, Victor Berdichevsky, whom I mentioned briefly earlier as well. Just about 40 years back, close to half a century, he came up with what is known as the VAM, or the variational asymptotic method, which is a combination of variational principles that we just discussed uh, a few minutes back, and asymptotical methods, which was a separate body of knowledge or research in mathematics and dynamics that people were doing. And we, or he rather, he combined these two methodologies. His teacher was Sedov, one of the greatest mathematicians and physicists of our times. By our times, of course, I include the 20th century as well. So that is Victor Berdichevsky, Sedov's student and Hodges's mentor. And one of the things that he says, which is very, very critical for our entire course, is this particular statement. Of course, he has some real gems of or punchlines or punch dialogues, many of which I keep quoting every now and then to a lot of my research students. But this one is applicable even for you undergrads. Is that what he said? Is most fundamental law of nature revealed up to now, because there are many laws of nature, as we know, and many of them are fundamental. But the most fundamental, and which doesn't fail at all, and which has been revealed at least up to this point in time. There might be other fundamental laws we might discover, especially as we go deeper into particle physics and also dark energy, dark matter, etc. But as of today, this particular day in June in 2024, we are looking at the most fundamental law of nature as the law of reciprocity. And reciprocity of what? Reciprocity of the interacting entities, which are all physical. In other words, we already said anything which is physical means it should have certain boundary conditions. It has boundaries and therefore boundary conditions. Okay. If it is not bounded, it's, let's say, in time sense, it becomes eternal. In the sense of space, it becomes omnipresent. And any entity which is omnipresent or eternal is not under the purview of physics, it's under the purview of metaphysics. So we are focused and very narrowly looking at only the physical aspects, which is what we'll do throughout this course. And for that, we should know that there are boundaries and there are boundary conditions. And therefore, there are physical interactions that are taking place and which are reciprocal in nature. What does that mean? If you have one field doing a certain thing on the second field is doing the same thing on the first field in an opposite direction so that they are balancing each other out. And that's a beautiful symmetry that exists irrespective of the field, irrespective of the sizes that are involved, whether it is classical mechanics, whether it is quantum mechanics, whether it is relativistic mechanics, special or general theories. All of them are subject to this particular thing. So maybe if we discover dark energy, dark matter, what exactly they are, it's possible. It cannot be completely ruled out that this may fail somewhere there. But as of today, we have no proof for anything that we are aware of at whatever scale in length and time and speeds that are involved, that will fail this particular fundamental law, which is the law of reciprocity of the physical interactions that are there. That is the action of one field on another field. For example, the electric field on the magnetic field, or the electromagnetic field on the mechanical field. And within the electromagnetics, of course, optics is a separate part. Then the thermodynamic field, etc. Think of whatever you might want to, in whatever scales, they are all having this opposite and symmetric reaction. So Newton's third law is what is in the Indian tradition called as the law of karma. What you sow, you reap. You might reap some of them immediately. If I'm trying to uh, just try to bend this, it might break immediately if I apply large enough bending moment. So that's something that is having an effect almost immediately observable. But on the other hand, some things might take a longer time. For example, you're sowing a mango seed, and for the mango tree to come up, it will take a few years. It might take a different number of years for a coconut tree to come up. It takes a different time for a human baby to start off as a fetus and then come out as a baby. So all these have different time scales and different physical sizes, etc. But essentially, every action has an equal and opposite reaction. When that reaction happens, there could be a time difference between the two, and in what form it might take, etc. There might be differences, but essentially the resultant sum of all the actions that you do and the resultant sum of all the reactions that you face are one and the same, whether you're thinking of yourself as a physical entity or a metaphysical entity. This is always valid. And all microphysics equations, as I already mentioned, even in quantum mechanics, it's valid, even in particle physics, all those equations possess such a structure. That is that symmetric structure, what we call as the principle of reciprocity. And macro physics, of course, operates with averaged characteristics of the microfields. That's where the so-called micromechanics and macromechanics are correlated to each other. Though they might seem like entirely different physics, the learnings from micromechanics go into macromechanics and vice versa. And when you look at that, most of the quantities in macrophysics are operated with mm, averaged characteristics of the microfields. For example, temperature, is coming from the average kinetic energy of the system whose temperature you're trying to look at a given point in time. So that's what actually that macro physics leads to thermodynamics. So even though you might be studying thermodynamics as a separate course and mechanics or dynamics as a separate course, these are very, very intricately related. For the purpose of getting into speed with the terminology, the equations involved, etc., we are studying these as separate subjects, but actually they're all have built upon the same fundamental laws, and the most fundamental of them, as we just saw, is the principle of reciprocity, or the symmetric principle that is involved in terms of how the two bodies interact with each other, but it holds for infinite or very large finite number of bodies interacting with each other in many, many different ways through many, many different fields. So with this, I'll probably conclude today's class, but if there are any questions, I'd be very happy to answer them or try to see if we can find some resolution to anything that you might be thinking about. Please go ahead and you can unmute yourself and ask.
Yeah, I think so. Let's go to some.
In like a previous slide, you asked about Kroneker's delta, and I think you put the conditions is wrong. It's like you have I equals J, and that gets you 0. I think it should be I is not equal to J, and that gets you 0.
Yeah, sorry. Yeah, right. Yeah.
Okay.
Thanks for pointing that out, please. Anything else? Anybody?
I think we're good here. Thank you.
Okay. Sure. Okay, then I'll see you in person tomorrow at I think 11 o'clock in the morning. Yeah, you have an afternoon session of lab visits. This is to the drones lab of Professor S. N. Omkar. Hopefully, we'll all be able to make it and enjoy. Are there any comments or suggestions about the lab visits that you have gone for so far? Because we have this afternoon and also a couple of them next Tuesday before we start the industry visits.
They've been really good so far. We really enjoyed them. So thank you.
Okay. Okay, that's good then. Bon appetit. Enjoy your lunch, and I'll see you tomorrow. Bye.
Thank you.
Thank you.
Welcome.
you.
Welcome.
Wonderful history covered, sir.
Oh, thank you so much. Najib. Thank
I
you.
never expected this much. It is enlightening.
I appreciate that feedback. Thank you so much.
Yeah.
I'll see you tomorrow, Najib.
Sir, yes, sir.
Take care. Bye-bye.